Hello. The way this interview went was very interesting to me for a number of reasons. I spent a lot of the time preparing for this, trying to figure out a few things. Manuel and Lenore Blum are two incredibly accomplished theoretical computer scientists. And I thought I could figure out a little bit about what I wanted to know of them by asking them questions about how they thought about their research. They both talked about this before. My friend Sean Hahn wrote a wonderful profile of Manuel Blum in the MIT Technology Review. Ben Brubaker did a Q&A with Lenore for Quanta. And a number of things come out about these two. Manuel describes himself as an engineer and not a particularly good mathematician. Lenore says that she is a mathematician at heart. And somehow these two have individually and as a pair been some of the most prolific computer scientists you could imagine. In his profile of Manuel, Sean was trying to tackle this question: how could a single person not just accomplish so much himself, but produce so many accomplished students, among them Michael Sipser, Luis von Ahn, the Vaziranis? And Lenore, also an incredibly prolific researcher, was an incredible advocate for transforming the culture of and bringing more women into computing. As I said at the start of this intro, I thought I could figure something out by posing direct questions to Manuel and Lenore. But there's a quotation from Sean's article that I think highlights something that kind of applies to them both. Sean wrote of Manuel, he is not so much a magician who refuses to give away his tricks, as one who is himself astonished by what has been conjured around him. What I think this quotation evokes for me is that of the great scientists, the great artists, as we try to conjure up pictures and understand them and craft our own visions of what must be going on inside, we often discover that they are as much mysteries to themselves as they are to us. And so it makes a lot of sense to me that this interview went the way it did. We spent much of the time talking about their current work on consciousness and the Conscious Turing Machine. I think that observing them talk about these ideas and play with the different implications is all I could do to begin to form an understanding of what I was trying to get at in perhaps a different way. I think you'll find their work very, very interesting in and of itself, but I also hope you take away something from the energy and care and thoughtfulness that they put towards their work. And now, Manuel and Lenore Blum.
Okay, so what got me into consciousness? I should say that I was born in Venezuela, and my parents spoke to me in German. And so my first language was German in a country where everyone spoke Spanish. No one spoke German. And then I came to this country, and people did not like to hear German spoken because they were at war with Germany. And so my parents decided to speak to me in Spanish. This was in the Bronx at a time when nobody spoke Spanish in the Bronx. Now it would be different, of course. Um, when I got into school, I didn't know any English. And I remember in the second grade being given a test of sorts where it said, look at the colors and I just didn't know the names of the colors in English. I didn't know any English. And so my mother and the teacher had a parent teacher meeting, and the teacher told my mother, I may get through high school, but she should not expect that I can get to college. And this bothered my mother, but it didn't. What bothered me was that I wanted to be smart. And that was pretty awful. So I asked my dad, what can I do to be smart? What can I do to remember stuff? Nothing would stay in my head. What can I do? And he really didn't have much advice, but I kept pestering him until he said, if you understood what's going on in your head, you could be smart. And I thought, that is such a wonderful idea. Really wonderful. And so I wanted to do that. And I remember taking out books from the library, but not much was known about what's going on in your head. And I remember in fourth grade, walking in the garden, trying to think about what was going on in my head. But all I could get was, it seemed as if there were a homunculus inside my head looking out through my eyes, and that to understand what's going on, I'd have to understand the brain of the homunculus. Uh, and of course, I knew that would not work. So uh, I did want at that point to understand what's going on in my head, and so that's where things began.
The thing I wanted to ask, and the way I'd been gestating on starting this interview, was this kind of arc I've seen of, for especially you, Manuel, but both of you, consciousness being the big, deep, meaty problem that you really wanted to get your arms around at some point. And now the two of you are finally doing it. And it took some time for me to understand, especially for you, Manuel, how your understanding of your own interests was TCS, theoretical computer science, was this thing you focused on for quite a while and did incredible things in the field, but still had consciousness in the back of your mind, as it were, as the thing you really needed to work on.
Yeah, I'll keep on going with, continue going with the story. I did want to understand what was going on in my head. My parents had told me that I should be an engineer, and I actually did manage to get to college. I got into MIT, which was very nice, and MIT was incredibly difficult for me, incredibly difficult, and at some point, a friend of mine, Bob Hertel, came by and saw me memorizing the stuff in my physics book. Because in the physics book they derived equations and then they put a big box around the solution. That I would memorize that. That was the only way I knew to think. You just memorize. That was true of my parents. That was true of me. He said, "No, you don't memorize."
So I want to just interject one thing that Manuel went to a military high school. And in that school, I think he was taught to memorize and just follow orders. So I think he picked that up when he was studying physics. Just want to give some background there.
Right, right. I didn't understand how to do it, but this friend of mine came by and said, "You don't memorize. If you need an equation, you derive it, from first principles." And that was a big eye opener for me. Nobody had told me that. I didn't realize that. My first grade in physics at first semester had been a D plus, and after he told me this, my grades started to go up. It made a big difference, and I began to really enjoy physics and math and the engineering. What a difference! So, uh, uh, but I was interested in what's going on in my head, and I fortunately I was able to take a course with a wonderful professor named Richard Schoenwald at MIT, and with him we started studying Freud together. We actually, in a year's time, went through the 20 of the 21 volumes of the standard edition of Freud, and that was on the side while I was doing the engineering, and that was an attempt to try to get an understanding of what's in my head. So this fellow, this Dick Schoenwald, uh, uh, saw me uh, saw me at MIT at some place, and stopped me and said, a wonderful man has come to MIT. His name is Dr. McCulloch, Dr. Warren S. McCulloch, and you should go and introduce yourself to him." He also told me that this man was anti-Freud. And so I did go down and I introduced myself to him. I thought I would talk to him, and that was interesting. He said, I told him I wanted to work with him. He said, well, after you read these books, he had an encyclopedia of books. After you read these books, come back. And I wasn't about to read those books, but I did read McCulloch's papers, and they were wonderful. They, they really were some getting into what I wanted. McCulloch and Pitts were the ones who defined the formal neuron. They were the first to do that, and to prove that you could build a Turing machine, a computer, out of these formal neurons. And so this was great, and I managed to prove some theorems about that, and then McCulloch took me in, even though I hadn't read anything else. But that was enough of that. And McCulloch was absolutely wonderful, a fantastic, fantastic mentor. He 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 was supportive. There was a real love there. He was very supportive, and he enabled me to do just about anything I wanted to do. Until about a few months later, after I started working with him, that he told me that I told him I want to work on consciousness. And for the first and only time in his life, he said to me, "You will not work on consciousness." And I remember his finger and the strong word "not," and it really shook me. I had never before gotten this negative from him, and never again would I get such a negative. I was not to work on consciousness. And Walter Pitts came by and told me something I already knew, that you got a thick skull there. You can't go in and do experiments to find out what's going on in the brain. All of which I knew. No consciousness. What they didn't understand is that I wanted something that the 4-year-old could understand. I didn't want the circuitry of the brain. I wanted to have some sort of higher level understanding of it. And uh, but I wasn't allowed to work on it there. Uh, One of the wonderful things about working with Lenore on consciousness is that I feel that we have the answer that the fourth grader wanted. We could tell that fourth grader what he wanted to know, and that comes out of this conscious Turing machine that we have defined. It's a very high level view of what's going on in the head, and it's been wonderful for us. Lenore.
I just want to say, I think Daniel asked you, had it, after all those years of doing theoretical computer science, having all these amazing students and all of that, what prompted you to go back into looking at consciousness in the brain? I think maybe, am I rephrasing it correctly, or?
I think that's a good rephrasing, but if it's okay for me to actually work our way there a little bit more incrementally first, because I have a couple of questions about the initial McCulloch episode that you just related. And there are two things. The first one I'll ask is about the Freudianism and anti-Freudianism, because I've heard you describe that before, McCulloch's anti-Freudianism. And I want to understand a little bit better how that struck you at the time, where you were initially reading lots of Freud, and then you encountered this great mentor of yours who came from a different perspective, and what it looked like for you maybe to wrestle with those ideas, or did you feel like it immediately made sense to you when you came across the way he thought about Freud? Like, what was that like for you?
So let me point out first how much against Freud Warren was. I called him Warren. Lenore and I both called him Warren. And Freud had written a paper called "The Future of an Illusion," McCulloch had written a wonderful paper called The Past of a Delusion, referring to Freud. So he was strictly against Freud. For me, I had always felt a little queasy about Freudian psychology. It was not hard mathematics, which is what I wanted, and there was a chance to get that hard mathematics working with Warren. So is that you wanted to know how once I had read some of the papers that Warren had written, I realized that this was where I wanted to go. This was beginning some hard mathematics and it was, going a step beyond. I felt beyond what Freud had said.
That makes sense. The second question I wanted to ask, and I think this will bridge into a later question I have for the both of you, but I think this one is more specifically for Manuel. It really strikes me. I've heard you relate a lot of the story in a number of different interviews and a number of different places. And what struck me about the way you just related this McCulloch episode, this story to me just now, is you don't sound rehearsed and you sound just as there's a lot of energy in the way you're telling it to me, and I feel that energy across every time you tell this story. And it's interesting to me how that doesn't seem to dissipate for you. It's like your admiration for McCulloch and your excitement and your memory of that excitement that you had at the time, it doesn't seem to fade. And I can kind of see why, but I'm wondering if you have any reflections on where that comes from, or if you have any theories about why is it that every time you tell this story, it feels almost like you're telling it for the first time?
Warren was the most wonderful person I have ever met. He was supportive. He was really somebody who loved both me and Lenore. We both knew him, and it was just one of the questions that might come up is, how come I've had done so well with the students, and part of it is just realizing how wonderful it was for me to have Warren as a mentor, and I had many other uh, people that were warm and wonderful, and it's from them that I really got energy and strength and could move on. Lenore.
Yeah, I think also there's something about Warren was so totally larger than life in every way you can imagine. If you use it, people use the word polymath for various things. I don't think it applies to anybody we've ever met except Warren. I mean, Warren was a poet. Warren was an architect. Warren was a psychologist. Warren was a neuroscientist. Warren was a mathematician. He was a philosopher. And he was tall. He had this, beautiful, smiley eyes. I don't, any picture you see of him, you just see these smiley. He was just so in love with life and everything about it that anytime you were around Warren, you just felt, wow, all the potential that you could be. The other thing is about Warren, which is so very different than anybody in academia or than academia itself. Manuel said when he went in to see Warren, Warren said, read all these books, but, really it came down to Manuel coming back with, really showing that he had looked at Warren's stuff and proved a theorem. So for Warren, it wasn't credentials that mattered. Is if you were interested in working with him and you showed that you had, a passion, he picked up on that and he let that fly. And I think that was, I remember one really, these sometimes some of his stories were accurate, weren't quite accurate, but they gave you a feeling for what he was looking for. I remember he came back. So I met Warren. So I want to say one thing about Manuel and Freud. Manuel and I had met when we were very young, but he's younger. He's older than me, 4 years. And so, yeah. So when Manuel came back for my high school graduation, he had just graduated as undergraduate from MIT, and he had just that last year when he was a junior working with Warren. And Manuel was still talking about Freud when I met him. When I was just graduated from high school, and we would go to bookstores and buy philosophy books. But I was so down on Freud myself because my mother was a scientist. My parents were very scientific, and I didn't see that Freud had anything to do with science. So I remember spending part of the summer also talking with Manuel anti-Freud. So I don't think he was quite anti-Freud that time. So that's one thing. But let me tell you this story about Warren. So I remember one time Warren goes to San Francisco to a medical conference. And he comes back and he says, I met this amazing kid there. He was the janitor at the conference, and he's so smart. I'm going to bring him back to the lab. It's just like the Will Hunting, good Will Hunting story. Exactly that. Turned out, probably this kid who we later met was a student, and he was just working there to get free entrance into the conference. He wasn't a real, but that's how the story was. And in a way, that excited Warren. If you had a passion and you were coming from someplace else, you didn't need the credentials, as far as you can tell. So it was so different. He accepted you for what you were. And you want to say a little bit, Walter, but I want to say in terms of Manuel, he accepted Manuel for who he was, and he saw the brilliance. He saw this I wouldn't say strangeness of Manuel, but that Manuel was already wanting to look at deep, deep issues, even though he was an engineering student. He wanted to look at deep, deep issues, and that captured Warren. And I think that Manuel, blossomed out under that. And I think that's why the story comes out, because that was, in a way, Manuel's intellectual birth. I would say that experience. Warren was the intellectual father that Manuel never had. And I think that's your intellectual birth, and that's why it keeps on. It's so important in Manuel's
and
life.
and Lenore was enormously important. Uh, I mean, first of all, she didn't especially like Freud, and we could talk about stuff, all sorts of wonderful stuff. For example, when I was at MIT, I was very religious. I went to sleep in the palm of God's hand every night. And Lenore was absolutely, completely atheist. And I remember, when you believe in God, there's always this bit of doubt that comes into you. And so I remember talking to Lenore about it and wondering, do you really not believe in God? And she said, yes, I don't. I do not believe in God. And so I decided, look, I've got to get a handle on this. I told God that I would not pray to him for a whole month. That I well, of course, the wonderful thing about switching is that the doubt went away. When I was in sleeping in the palm of God's hands, there was always a bit of doubt. When I left, there was no longer that doubt. It's one of the reasons that I stayed out completely. Lenore was very important to me. I mean, she's the one, for example, that knew that I was really interested in consciousness, and that told me about 15 years ago, look, Manuel, you couldn't work on consciousness before; nobody would take you seriously, but you can do it now. So 15 years ago, she said, times have changed. We do know something about consciousness. Let's go back into it. And that was what really important. And it's an example of how Lenore actually has guided me. It's, and the work we're doing together is really a work that we do together. Lenore comes at it from her point of view. I come at it from mine, and they are wonderful. They join together, and we get more than either of us alone could do. Uh, so you asked about, well, what this, I was in this. Let me just mention that I was in engineering, which, after all, does make sense. I would not have. Okay, so I was in engineering, but later on, I went and I got into mathematics. The particular part of mathematics I got into was logic. And the reason I got into logic is because I thought that that was the mathematics that would help me to understand what's going on in the head. And let's see, so what else? So um, I lost my train of thought. Uh, right. And in fact, I got into something called recursive function theory, which is computability. Again, it's computability. I thought that would be what would help me. And uh, then I was very fortunate. I had this a wonderful professor, Hartley Rogers Jr., who wrote a great book on recursive function theory, which is what computability was called. And so I was very lucky to have that. And then there was somebody who came down to see Marvin every so often named Marvin Minsky. And Marvin would come when he had some sort of theorem. He'd come and he'd show. He was wonderful, and he eventually became my thesis advisor. And Marvin wrote a book called Finite and Infinite Automata, a wonderful book, and it was essentially the same stuff I had gotten from Hartley Rogers, but from Hartley I got the mathematics, the logical approach, and from Marvin I got the more engineering approach. And so these two really combined um, gave me something that I really wanted to get into.
I'm thinking about the way you both just talked about Warren McCulloch, this element of almost you had this direct experience with him and you were willing to continue relating the stories. And so there's this, you want to preserve the memory of him. And he also seems like the sort of person who could very easily be mythologized. And I think a lot about this perspective, especially I think in light of Sean's profile of you, Manuel, the way in which it's creating this experience, like this experience I had of you as a person. And I start to wonder, what is the gap between Sean's telling of your life and then how you look at your own life? I'm curious how you two think about this in the light of you two are now, these incredibly accomplished people with things named after you. The Blum shub, like random number generator, the Blum speed up theorem. These are all things that are named after you. You leave kind of traces of yourself in the world. And it's very easy for somebody like me to kind of come along later and pick up these pieces, pick up the stories, and then fill in the rest with my own imagination to form a complete picture of who the two of you are. I'm wondering how you think about that process of mythologization, if that makes sense, for the people you've encountered who had such a big impact on you.
Can I say some words about Warren? I'd like to say some things. First of all, I think that we're not mythologizing. This guy was larger than life. And in fact, for me, what was interesting is he never, during, as far as I know, people loved Warren and they acknowledged him, but he never, even when he died and, afterwards in those years, at the beginning, nobody seemed, people would talk about others, like, I'm just thinking of course, Wiener, of, not Wiener, but yeah, Wiener, cybernetics, um, Shannon, um, von Neumann and others. And Warren was never in that group at all. And I was sort of shocked. In fact, he sort of died out. And it's only in recent years when people realized the McCulloch-Pitts neurons were really essential for neural nets that are so important today that he's come back. And maybe there's some, if there's any mythology, it's probably much less than who he really was. He was this larger than life. And I used to think, why is it? Why is it that he didn't get that kind of recognition? And I think it was because he was so un-establishment. he did start things like cybernetic societies or whatever. I can't remember what the Macy, conferences, but he wasn't like active in a professional organization trying to be president of this or that. He didn't develop big labs. And I remember, he did this work on what the frog's eye tells the frog's brain, which was really the precursor to the Hubel Wiesel work on the cat's vision, which they got the Nobel Prize for. And he wasn't, and he wasn't, or Letfin wasn't either, who was in that same group, weren't really given the same recognition. And it's again because neither of them had large labs. They never, orchestrated large labs where their name was on top and they had 50 million people under them and they would always be the first author on this and that. They weren't like that. They were so down to earth, these people. They were so approachable, and they were just there for the science, and they were just there to encourage young people. They weren't there to build themselves up professionally at all. And I
So
think
Lenore mentioned Jerry Letfin. The people around Warren, the people who came down to see him, were all very approachable, very warm, really very much like Warren. They were like him, and in fact, the success I've had with students is largely because that's what worked for me, and I tried to do the same thing with my students.
Right. So, for example, Jerry Letfin and his wife Maggie became the house parents of one of the dorms at MIT. And all these people were just there to encourage young people and just delight in the idea of their science and get others excited. So I think that didn't come across in terms of the publicity. So I think anything that we're saying now that might seem to mythologize them, I think it's even understated. I think is totally understated, my view. And I think that's how I see it.
I think I maybe framed that question badly because I did not mean to say that you were mythologizing McCulloch, but I guess I guess maybe what I was trying to say or wonder at there was, do you two consider or worry about being mythologized yourselves at all? Is that ever something you've thought about?
What I really wanted to be able to tell that fourth grader what he wanted to know. That is the important thing for me. And let me mention the following: that when Lenore told me I should get back into consciousness, she also told me to read Bernie Barr's book. And Bernie Barr's book is the one that introduces the global theater of, as a model for what's going on in the head. It's a very simple model. He views what's in your head as a kind of a theater with a stage and a play going on and an enormous audience of people watching what's going on. And these are the processors of the brain. What's wonderful about this for me is that when I heard it, it's very simple, and yet when I heard it, I realized that's what I was looking for. That is what the fourth grader wanted. And since then, the work that Lenore and I have done is to use our knowledge of theoretical computer science, its approach, to in fact make a very simple model of this theater that Bars talks about, this global workspace theater.
So, Manuel, I see you're going to our research, and I can continue with that. And maybe let's do that for a little while because that's where our heart is right now. We can reminisce, and we will. I can't. We can reminisce too. There's a lot to reminisce. For example, let me just say one thing before we get off Warren. Warren had a farm. He would always invite us to his farm where he built most of the houses on the farm. And at his house, he could have everybody who came to Cambridge stay with them. People would come to dinner. And as a young person in the, and I was still a student, undergraduate and a graduate student. I was so inspired by that. I thought, well, maybe that was something we should do. And for a number of months, every night, we would have the whole lab of young people at our house for dinner. And here's while I'm an undergraduate and a graduate student, and I'm doing this too. And it was great, and we would have so much fun. And it was so great, but I got so exhausted with that I never cooked another meal after that. We ate at a paper place. My son had to do his own cooking. I don't have, I don't. We don't have a dining room. we, whatever. So anyway, but that was a huge influence on me. But let me get back to the conscious Turing machine because it really has two real. We're inspired by two things. One is, as Manuel mentioned, the Bars Global theater model, Bars's theater model, and that was one of our big inspirations. And the second, which one, the reason we call it a conscious Turing machine, is what we were looking for is also, as Turing had found a very, very simple but powerful model of computation. We are looking for a very, very simple but powerful model of consciousness. And in that way, it's an analogy. But our model is not a global workspace model at all. I mean, it's influenced by that, but it is more. And it's not a Turing machine either. And it's not a model of the brain either, because it's just too simple for that. So even though we're inspired by all this, and we are inspired by cognitive neuroscience, um, this is not a model of the brain. It's not a Turing machine, and it's not a general global workspace because we require more.
But it is a simple and formally defined, a mathematically well-defined machine.
And that is the analogy with Turing, because the Turing machine is so simple. It doesn't have the bells and whistles of computing in the cloud, supercomputer, whatever. But whatever you could compute in the cloud, you can compute in this simple Turing machine. And if you can't do something on the compute something on the simple Turing machine, you can't do it in the cloud. But you can get your head around this Turing machine, and you can prove what can be computed, what can't be computed. Very hard to do. And that's exactly what it's very hard. It's very important for people to be looking at the brain. The neuroscience works are great. That's very hard to do. And we're trying to get the essence here of consciousness, something, a machine that will have the essence. And I think that we're getting, I think, kind of close. This newest little chapter that we've written, which conscious AI is inevitable. One of the reasons for that is, even though the machine is so simple and it's formal, it does align with a lot of the major theories of consciousness, which, as you might know, are sort of fighting with each other right now, that this is the right theory and that's the right theory. There was the big debate about the global workspace versus IIT was one of them, but so many other major, by really great people, theories. And in some sense, what our simple CTM is sort of saying, hey guys, these are just looking at different aspects. They're compatible or they're complementary. They don't have to fight with each other. It's like looking at different aspects of the elephant. It's different parts, and each of them are important. We're not saying they're not, but in fact, we're able to show that our simple machine has a lot of, at least at a high level, has a lot of the properties of the major theories. And I think that's really interesting. But the next conclusion, at least for me, and I don't know if it's as strong for Manuel, is that if a simple machine model, very simple, aligns with a lot of the great thinkers, that also gives, more confidence that this AI is going to happen. This AI consciousness is going to happen. Let's develop our idea a little bit more, maybe implement it. It's going to have, since it has a lot of these things. I mean, we believe it's important, but I think a further corroboration is the fact that it aligns with most of the major theories. I mean, I haven't gone through all of them. I haven't gone through, I think we have a paper that goes through maybe 8 or 10. I don't know. But, and those are ones that, all are really good theories. They're all great theories. And they're all, what one has to understand, but they fit together. So that gives me that's why I can come out with a sort of provocative statement. I don't know how Manuel feels about it, but that was my little.
No, so what I feel is that the wonderful thing about the model is that we ask question after question, we find a very reasonable answer from the model. Uh, I worked in this neurophysiology lab of Warren McCulloch, so I do know, and I was very interested in the brain, so I do know something about it. And uh, it the neuroscientist really is interested in the various parts. There are the people that work on the hippocampus, people that work on the amygdala. There are the thalamus. There are many different parts. Uh, what's wonderful for me about this model is that it's very high level and it enables me to ask and answer questions that come up. Questions that would be difficult to answer if you're only looking at, say, the thalamus. Okay, so
Well, for me, the model is okay. Let me just give you some more for me what the model does. So, I'm a mathematician, and I really was interested in math since I was really young, like 9, 10 years old. And one of the reasons I liked math, I realized, was first of all, I liked the fact that you really didn't have to memorize. I never, if you got the principles, you could just develop everything. And I wasn't good at memorizing poems or things like that at school, even though I got A's and everything. It was not easy for me. Those didn't come naturally, but the math seemed so easy and natural, and I liked the fundamentals. I also and I like the fact it didn't seem, in fact, in early years, I didn't understand how faddish math could be, but it didn't seem to depend on people's opinions or whatever. I like that. But another thing is, even though my mom was a science teacher and she was very interested in biology, again, I found biology very, very difficult because I couldn't memorize. I couldn't remember all these different things. It just seemed like a lot of things to memorize, and I couldn't fit them together. So, how does that deal with our model? So looking at the brain, for example, very complicated. And for me personally, our model gives me a scaffold to actually go back to neuroscience and see what people are talking about and see how they fit into our model. So it's given me a power to learn more neuroscience, which I never took any courses in, and to read the philosophy, what the philosophers are saying and all that, because I can ground it in our model and I can see where it fits in our scaffold. So that's another advantage for me of our model, the simple model. It's given me an education, so to speak.
we had a fun time. We we were professors at Berkeley, here at Carnegie Mellon. Right now, we are emeritus, which means retired at both those places. But we are actually professors at Peking University, visiting professors, and we teach there, and it's been wonderful because they are very, very wonderfully bright students there. And what we do is we teach them about this conscious Turing machine. And what's wonderful for me is we're basically asking them to look for something that they feel is missing from this conscious Turing machine, something that needs to be put in order to be able to be a better model. And in every case, when they want to change that machine, we can show that no change is necessary to to for the questions that they want to ask. And they have been, as we have been, quite happy with the fact that no change is necessary, and it's a very simple model.
But I think that we have to acknowledge that it's so simple that, in fact, and one thing that we do a lot is simplify. We're constantly simplifying. But I think that, it's true that there will be things that come up that we can't answer here and that we will have to think more deeply about. And I think what's happening is it's helping us focus. And particularly with these students, that's been so wonderful is that they're like a sounding board for us because they don't mind, coming up with all these ideas and saying, oh, okay, well, let's do it. You can't do this in your machine. And they give us the thing and then we can sort of go through it. So they've been wonderful. Um, in being that sort of crit, immediate critiques for us that we can deal with, and so it's for our research. It's been really very helpful having these students. We actually started teaching this course as our last course before we retired from Carnegie Mellon at Carnegie Mellon, and that was really fun too. So we've had, in fact, we had about 4 professors in that class too, with undergraduates and graduates. It was really a fun course. And then so I would want to say some things that has helped our research. It's kind of ironic, but so we'd started working together on this. I know, Manuel, was about 10 years ago, but when we really hunkered down was when we retired, and we didn't know this, but COVID was just to start. We didn't know this, so we retired. We left teaching at just the time when it became so difficult for our colleagues to teach during that period. Teaching during COVID was really hard. You have to get new methodologies, and we were immune to that because we weren't in class. And in fact, our teaching in Beijing was over Zoom, so that worked out okay. So first of all, we didn't have to deal with the physical thing of teaching during COVID. Again, we were locked in together. We couldn't go out very much, and here we are together and working together. So day and night we're working together. So that was kind of lucky. Nobody could invite us out to eat or anything like that. We were just locked in wherever we were. We were together.
And that was wonderful. We didn't realize until later.
Yeah, day and night we were working.
Found it very difficult. We worked together very well.
But there's another feature that was really important, at least for me, and that was Zoom, because a lot of the associations or seminars were going online all over. And I started to join seminars that were coming out of Europe, that were coming out of Asia. There was a whole lot of work in consciousness. And in fact, there was a group that was coming out of Oxford and Munich that were mathematicians looking at consciousness. And I got to somebody told me about it. I went online, and every so often, even though I wasn't part of that community, I would say something, and they accepted, they brought me in, and I got to know people working in this field from, mathematics, from neuroscience, from philosophy, all over the world through Zoom. And if I had gone, now we do go to the conferences, there are several major conferences in consciousness science. If we had gone before, this Zoom thing, if I had gone in, nobody in this community would know me. And I'd just go say, I'm a mathematician interested in consciousness. I'm interested in talking to you. You think anybody would talk to me? Probably not. I wasn't known there in that community at all. But through this Zoom connections, Manuel and I got to know so many of the key people. And we go to the conferences now, and they know us. And now, in fact, I'm president of this association for math consciousness science, and which is kind of incredible to me. So it's kind of like fun, because that organization was started by some young postdocs who were really passionate, mathematicians who were passionate, math physicists mostly, what they were doing. And they started this sort of seminar series organization. And I remember they had to, become official, and they needed a token president. So for this official things, they asked me, Lenore, would you please, maybe we could just use you as, the inaugural president. And I said, sure, why not? I've done things like that.
You're much more than the token president.
I'll do it. And so, okay, I did that for a year. And then they had an election, and I got elected. So I'm part of that thing too. So the irony is that COVID really helped us a lot in a lot of different levels here. So it was, we were retired. People might not have known us. And yet now we're, really very involved with this community. And really, for me personally, this is one of the most fun things I've done in my life. And it reminds me a lot of, my early days. And I think that's why we're going back to our graduate student days.
So this is great for Lenore, because she really is getting to know what's going on and to be a part of it. I personally was not so interested in that. I just wanted to be able to tell that 4th grader what he wanted to know. and that's yeah. So that's where I'm coming in. In fact, I should mention here that there are a couple of questions that come up in this consciousness study that really came up in those very early years that I wanted to understand. One of them was uh, had to do with free will. There is Sam. So here's the problem. Samuel Johnson uh, stated the problem of free will like this. He said, "All theory, or all science, is against the freedom of the will. All experience is for it." And that's a paradox. It's a wonderful paradox. Uh, Samuel Johnson lived was born during Isaac Newton's life. He was uh, 15 years old when Isaac Newton died. He knew that wow, from F equals ma, you can explain what's going on. That science was wonderful in that way. So when he says all science is against the freedom of the will, he means that in a deterministic world, which is what it seems to be, at least at that time, in a deterministic world, there is no free will. Everything's determined. God, who has created the world, knows exactly what's going to happen. No free will. On the other hand, you know that you have free will. You know, and this is a really bothersome question. What's going on there? And one of the wonderful things about this model and the simplicity of it is it helps me to understand to answer the paradox. We have an answer that we believe Samuel Johnson would have helped Samuel Johnson would have helped him understand what's going on there. That's one. So understanding that free will problem was one of the problems that I really wanted to answer, and another one was a problem which maybe Lenore is not so happy with, but it really bothered me, and that is how does the body generate the feeling of pain? Uh, so, so this is something if you don't have God, if you don't have soul, if everything is just machinery, how does machinery, which is what we feel we are machines. How does this machinery generate this feeling, this agony that comes of pain? And I can sort of explain it a little bit better, maybe by pointing out that there is this disorder called pain asymbolia, and people who get people who have pain asymbolia will know when they have pain, but they don't suffer. There is no agony associated with it. And children, when they're born, if they're born with pain asymbolia, they don't live very long. There are some exceptions, but by and large, they die by the time they're 3 years old. They start off by biting their lips off. They know they have pain, but it doesn't cause suffering. And so pain asymbolia is interesting. You can get it also from a conk on the head. So a person gets a conk on the head, he can become pain asymbolic. And after that, he will know about pain. He knows about pain because before the conk, he knew what it was to have pain. After the conk, you can put a cigarette out on the palm of their hand. You can put pins through them. You can do you can take a bucket of ice water. I can put my hand in a bucket of ice water for 30 seconds, but not more than that. They can just put it in and leave it there. They know it's painful, but it doesn't matter. So the question is, to my mind, is what's going on? What is it in the head? What is it that's generating that agony? It can't be too complicated because it's just a conk on the head and the person has it. What is it? Our robots are pain asymbolic. We know how to make them look like they're in pain. We can We can do that. We can give them essentially these the ability to feel pain, but you know that they are not suffering from it. What is missing? What would one have to get? How can one make the robot actually feel the pain? Lenore, uh, uh, Lenore, Lenore is very bothered by this because she says, "Well, why do you want to give pain to a robot? Why would you want to make a robot feel pain?" But actually, it's very important for humans to feel that agony, and it is important also for robots. Uh, Go ahead.
So, two things. First of all, I see that, Manuel's just brought up free will and pain. And those are two things that are very emblematic or symbolic of what's called phenomenological consciousness, subjective consciousness. So, consciousness, first of all, means different things to different people. And I think David Chalmers, with the heart problem, sort of put it in two buckets. There's what is more cognitive, what he might call the easy problem, the cognitive access part, the part that's much more computational. And the second part is the part that's phenomenological, subjective feelings. Okay. So I think really most people's ideas come in these two parts. And what we would like is the CTM to really exhibit both of these. So I think the part that is access consciousness or cognitive consciousness, I think people agree that, we have it, everybody in our model will have it. The part that's subjective is really what we're really trying to get in the model too. And that's when I said before that the first part we might call attention. It has to do with the global workspace. It has to do with the theater model. But when I give a talk, I say attention is not all you need. You need something else. And you need something else to explain this phenomenological thing. And it has a lot to do with how our model, CTM, develops world models, models of its internal world, its external world, where it fits in its external world, and how it labels things with a very rich multimodal language, which we call Brainish. And that's where a lot of the phenomenological parts coming in, where you have a word in Brainish, for example, you could see a rose, and that might be just your vision processor saying, oh, I see a rose. But if you smell the rose and you touch its soft petals and you see its bright redness, that in our model gets fused as one word. It's one word which has the various different modalities. It has the senses of eyes, of sight, of smell, of touch, maybe taste. You might taste rosewater, so all of that's fused together. And that's going to be very important in terms of the phenomenological part of the CTM. And that aspect is missing in the global workspace or the traditional theater model. The theater model is very good for access and attention. For awareness, you need more. You need more. So that's things we grapple with and we're working on a lot. And how this fits in, it's going to be a little bit more, maybe not complicated, but we have to understand it better. But certainly the Brainish, succinct Brainish words that fuse modalities and the ability to make world models is which are sort of sketches. When Manuel was thinking of this homunculus, yeah, we have something like that, a vision of a model of ourselves, but it's kind of a sketch. And inside that, what happens to the homunculus having a homunculus inside? Yeah, there's a sketch, but it's actually diminished. And it just goes a few iterations until there's nothing really there. So it's not like it's going to go on forever at all when in this model. So okay, so one of the things I wanted to say was Manuel was getting to, with pain and free will, to a little bit more of the phenomenological part of the model. Second of all, I wanted to say about pain. I think Manuel is very right that, humans without pain, the kids that are born without pain have a hard struggle staying alive, and many of them in the past haven't. I think there are ways of treating or knowing about this that keeps people alive. But in the past, no, these kids would just, break limbs, have to have their teeth removed, all sorts of things. So Okay, but there is a reason to have things like pain, and I think that a lot of the discussion about consciousness and robots and why would we want to have them suffer, um, well, you know, empathy. A person without empathy is going to be a sociopath, and a robot, the conscious robot without empathy, is going to be a sociopath. Well, maybe that with empathy, it's not going to be our empathy, but we might want it to align with our empathy or whatever. But without it, without this kind of suffering and empathy feelings, we're not, these are going to be really, monsters. They could be. And I think that is a reason why you want to have consciousness, at least you want to have consciousness. Without consciousness, you're not going to have empathy. And, the pain aspects might and might not be important there as well. So I used to be very down on Manuel for talking about pain. And so I picked up the issue of how do
Ooh,
you
how
view
wonderful.
pleasure. That's what I look at. But I understand it much more now. Yeah, so he sort of won me over there.
Mhm.
Hey, did you know that? Anyway, I think I made some points there that I was trying to make. Hope they were clear.
That's helpful. Well, I have a bunch of questions for you both around different adjacent questions that come up in some of the questions you're looking at with consciousness. One that I've thought about a lot was the multimodal interlanguage you speak about, Brainish, was really interesting to me because it kind of connected to actually a realization of Manuel's that was mentioned in Sean's profile about not needing language to think. And this also came up in a conversation I had with Ted Gibson, who is this linguist at MIT. And he is really interesting to me because of the way he thinks about a lot of this. And I think one thing he mentions is that he actually doesn't have an inner monologue. And that's a pretty different experience from I think I have an inner monologue, but one of the things that kind of came up as I was talking to him was this example of me thinking about, well, we don't always seem to need language to think, but it does seem like something of an initial crutch. So, for example, when I was first learning the violin, for instance, I had to think in words to myself about where in the world are my fingers supposed to go when I'm playing this note. And eventually it becomes more automatic and the language begins to slip away. I can just view the thing on the page, my fingers go in the right place. And so that was kind of interesting to me. And there's this evolution of, maybe if I'm to put it in your terms, the internal language that's being used and the different multimodal components that go into that language. And I'm curious how you two think about that.
So let me mention that, I had said that my first language was German. And then in the Bronx, my parents switched to Spanish. And I remember the shocked look on my mother's face when she realized that I had lost my German. She pointed to the window and said, "How do you say window in German?" Fenster, Fenster, gone. German was just completely gone. So there was a little while in my life when I no longer spoke German and I didn't know much Spanish at all. And I wondered then, how am I able to think? I didn't have German and didn't have any Spanish either, or very little. Yet I felt I was able to think, including these thoughts that I'm mentioning now. How I was then asking myself, how am I able to think this? Well, it can be done without language.
So there is some research. There's a woman, Ev Fedorenko at MIT, who has done work on separating thought and language, because for years that was like photo and all this language and thought were sort of fused. And so one has this thought. Multimodal doesn't necessarily mean English. I mean, we're fusing sounds and, it could be all sorts of things. So maybe this person who doesn't think in a language like English, which we do, your inner voice is usually in the language you're talking about. That's what most people see it as. I'm wondering if this person what their dreams are like. Actually, that would be very, very instructive for us, because we see dreams. The act of dreaming is very much like the act of being conscious. except for several things, except, your input and output are essentially cut off. So dreams can be fantastical. Nevertheless, they're very similar to, because the dreams are a lot of frames, like in a movie. They're framed, and that's, when you see something, you're seeing us. You're not seeing it all. You're seeing just a gist of this. You have a very short description of it, and then you fill it in when you need to, and that's how your dreams are doing. You're not. I mean, how come you have color? You have color in your dreams, and people walking around and doing all these things. You're not seeing it at all. You're creating it in your brain, and so dreams, the creation of dreams in your brain are very much like the creation of your world models. And I'm wondering how this person actually, what their dreams are like. I would be curious to find out. So if you talk to them again, ask them, do they dream?
It was funny that you mentioned Fedorenko. That's actually Ted Gibson's wife. So I'm very aware of her work, and it came up many times when I spoke with them.
Yeah, yeah, yeah. So I like that work because
Did,
they
did, did
separate.
you, what did you get from it? Did you get something?
Well, yeah, I guess it was more or less some of what I just spoke about to you, and that her experiments were basically denying this proposal from linguistics that language is connected to thought in the human brain. And I think that what she was trying to get at, not to say the experiments are conclusive, but certainly they seem to indicate something directionally, is that even during non linguistic tasks, so music, like I was mentioning, or maybe mathematics, the way you'd see that in the experiment is that the language processing regions of the brain would be activated even when you're doing music or a mathematics task. And since she found that there was no response in language regions of the human brain when they were doing arithmetic, musical processing, general working memory, other kind of non-linguistic tasks, the hypothesis coming out of that is that complex thought and language are separate and one doesn't require the other. I don't know that this is full consensus on the picture right now, but at least from these initial experiments, that seemed to be what she got.
I think what she's getting at, though, is that's not necessary. But I think that probably a lot of thought does connect with language. I think that there probably is. You can separate it, but I would suspect also. See, she's saying it's not necessary, and that's probably true. But most people might use both. Many people might use, for many tasks, you might use both, or need both for many tasks. Anyway, what I wanted to also say, though, is when you were talking about that when you're learning to play an instrument and you were thinking in your head and all that, that's very much explained in our model as well, very much. Because what it is when you're actually learning this and you want to coordinate your muscles, your fingers with the thought and all that, everything is going through consciousness. All of that kind of processing is going through the stage, going down. But after a while, connections are forming between your finger processors and your music things, and these connections, these links are forming, which may not have been there before. And after a while, you can then do this unconsciously. So in our model, because our model starts out as the baby CTM with no or very, very few links, and links form between these long-term memory processors. Maybe I should sort of suggest what the model is, because we haven't quite said it. In our model, what we have is a huge, you see what Bars talked about is you have an auditorium, a theater, you have audience, a large audience, and on the stage you have actors, right? And that actor has a script, and when the actor reads the script, it's being projected, broadcast to all of the audience members, okay? And every so often in his model, maybe some of the audience members want to get their information on stage to be broadcast down, okay? And they do some kind of competition in his model, and some script gets on stage, and then it gets broadcast out, very much like that. And in our model, it has those elements. We have a very tiny, what we call short-term memory, which is a little like the stage, and then we have a very, very large collection, like maybe 10 million, what we call long-term memory processors, which are very powerful processors. And at first, these processes we say are not connected. They're just start off pretty independent. They're potentially very powerful, but you could make them, specific to start with, and we do for now. But in the basic model, we probably want to have it start off as vanilla. Anyway, so what happens is we do have a formal competition for these processors wanting to get their information on stage, and we have a way, rather than saying they just discuss it and decide who gets up, we do have an actually very formal competition for their information to get on stage. And you might think of the one that has the information with the most weight, it's not quite right, gets on stage, and that gets broadcast down to all the. And then in our model, we say that conscious attention is the reception by all those long-term memory processes in the audience. Okay, so that's sort of how things go. So in fact, at first, everything when you're learning to play this instrument, everything's going through short-term memory because there are no links formed. And after a while, links form between different processors, and then you can sort of do your instrument without actually being very consciously paying attention to it, because nothing's getting up into short-term memory. It's all being done within the audience itself, within the audience of long-term memory processes. It doesn't have to get on stage. So that's sort of a little bit of the explanation of that. And I don't know if you probably heard from some of the talks, what example I give of what's her name. Have you heard that example to explain this? I can tell you.
Yes, yeah, I do think I remembered the examples.
Let me quickly this. I'll quickly do it. Okay, so this is a scenario. It's you're at a party, you see somebody you know, but you can't remember her name, right? Happened to you, and then you go home, and about an hour later, it pops up into your head, and what's going on, right? And you can't do anything about it, right? So what's going on is there's a processor that gets very embarrassed that you don't remember her name. It gets a message, puts a lot of weight on that message. What's her name? Gets into short-term memory, and gets broadcast down to all the processes. And another processor will say, well, you met her. Oh, you actually did an interview with her. Oh, and that gets up there. I mean, oh, well, no, you didn't, with her husband. Okay. And her name starts with E. That another processor goes up, and then we all remember it's Ev, whatever. And so that's kind of the process that's going on also with the theater model. So what we've added to the theater model was to be very precise about what's there. We've been very precise about chunk of information. We have that very formal in the model. We're very precise about the competition. We're very precise on how this whole flows. We're precise on how the links form. We're precise on how these processes correct. So maybe a processor made a mistake, said her name started with T, but it was really Ev. Um, there's something in the processor learning, what we call sleeping experts, which is due to Blum, which will lower the weights, will help balance the weights. So lower the weights if the processor realizes it made a mistake, but raise its rate if it actually was correct, but didn't have a high enough weight to get into consciousness, and so forth. So we have all of those very, very, very formally done. Um, and one thing that's really nice, and it occurs to me now to say this, is what is really different from our model. Well, there are other things with the world model, but from the CTM and the theater model, is we have no central executive. We have no stage director. We have no. It's the competition process works.
So that's important. That difference is important. Every other group that we know has a head. The orchestra has a conductor. The country has a president. All of these groups have a head. Our CTM, our Conscious Turing Machine, has no head, none at all. Everything is determined by the competition.
Right. There's no one entity that is omnipotent enough to make wise decisions. And actually, we can show that the structure we have with no central executive is really a powerful structure for doing AGI, artificial general intelligence, because to really hone in on really being able to solve things that, suppose there's a problem that it wants to solve. And if it's this central executive who has to decide who's going to solve it, that central executive might be not thinking out of the box, may not be knowing that some of these processors, or that it doesn't really know its capability, can actually work on it. So when it's the problem gets into short-term memory and gets I want to solve P equals NP. That's the one I use. And it gets into short-term memory. It gets broadcast to all the processors. And some processors that has the time or interest to work on it will say, hey, I know a strange mathematics that might work with this. Maybe you haven't used algebraic topology for this. And that will get up there and that will get broadcast, and other processors will think, that sounds interesting. Maybe I'll work with you on that. So it's a way of broadcasting this and identifying or actually enabling those processors that can actually work on it that you might not know about, that central executive might not know about, to actually come to the fore and work on the problems to solve it. And so we're seeing that this is really essential if you want to do AGI. It's not that central executive is actually limiting. It's not helping, it's limiting, is what we're saying.
It's limiting because the central executive really doesn't know if a task has to be performed. A central executive doesn't know what each and every processor is capable of. It doesn't know how much time they have. Doesn't know. When a task has to be performed, some people I've asked, how would you choose which processor does it? People say, well, maybe you have a special processor that keeps a list of all the unused processors, and when there's a task to be done, it gives that task to the first processor that doesn't have a task to do. This doesn't work. In fact, in the CTM, what happens when a task has to be done is that all processors work on it to the extent they have time and ability and knowledge. Some don't have time, okay, but to the extent that they have time and ability, they work on it. And okay, and to that extent, and one of these 10 million will get up on the stage with information it has, and all of the processors will get that broadcast. And half of those processors will realize they don't have what they have is not as good as what actually got up on the stage, and they'll stop doing it. They drop out. And then again, one of the remaining processors uh, will get up on the stage and it will have something to say, and half of the remaining processors will see that they don't have anything as good and they will drop out. And so very quickly, this whole competition reduces to one or a few processors that do the task, and the decision hasn't had to be made by some central executive.
The central executive point was especially interesting to me, and I have some questions for you about how you think about AGI in a second. But there were two connections that came up for me as I was first reading this part of your paper, and they come from two different directions. One is there's this very classic argument. I think it might have been Leibniz's, but it was kind of among the early modern, very empiricist philosophers who thought about this question of is there actually, something like for something like a mind, in the sense of we have all these thoughts, we have all these experiences, but on the empiricist picture, I have no justification for or evidence for believing that there is a singular container or something in which all these thoughts inhere. So I experience my experiences, but I can't experience or introspect whatever it is that's holding these experiences. And this can get really weird because if you take that empiricist argument far enough, then you start to lose the grip on whether there are actually boundaries between different people and their experiences. And then you end up with a situation where all of experience, everybody, it's just a scattered collection of thoughts or something like this. But that was kind of an interesting connection to your lack of central executive. And the other one I thought of was the more kind of similar to this, maybe a phenomenological take on it, which was I think certain people, when they are arguing that perhaps you don't have free will or something like this, will ask you to reflect on you're having a thought right now. You're going to have thoughts in a second. Are you exerting any agency in the thoughts that are coming into your head? And that seemed like an important connection to what you were saying about the lack of central executive. Both of those articulations feel interestingly consistent with your picture.
One of the interesting things about how the decision, so I'm talking about the decision of what gets up on the stage. Bars says that the audience members get together and decide amongst themselves what to send up. Uh, so when I say that our model is very precise and formal, I mean that I can't use this. He doesn't say how these people make that decision. Whereas in our model, that decision is made in a very precise way. It's very much like a tennis tournament or a chess tournament where processors play against each other. In the tennis tournament, A plays against B, C plays against D, and the winners then play against each other up until you finally have a winner at the top. So, uh, so processors do attach weights to their information, and they go through this competition like the one in tennis or chess to decide what will actually become the winner. The wonderful thing about doing this for the Conscious Turing Machine is that it turns out that this tournament, the CTM tournament, has a certain guarantee associated with it, which the tennis and chess tournaments don't have. The guarantee is that a processor's information will get up to the stage with probability proportional to its weight. And this is not true of tennis. This is not true. It's not true of chess, and yet it is true of the CTM. And as a consequence, because the probability of a processor's information getting to the stage is proportional to its weight, it doesn't matter where these processors are placed. They could be they can't be moved around in the brain, and so this is wonderful because it doesn't matter where those processors are. They the decision whether or not they will get up is completely determined by the weight of their information.
So I'd like to add something to that. So I think you alluded to experiments by Libet, which said that decisions were often made before you were conscious of them. Okay, and in our model that happens as well because you see the processors are putting chunks into the competition, and to get into short-term memory and to be broadcast takes a little time. And even though that process is pretty quick, Manuel was talking about this like tennis-like tournament, which really, if the 10 to the 7th processors takes about 7 steps. It's very quick because it's a binary kind of competition. But nevertheless, there's a little delay. And depending upon how long a clock tick is in our model, it could be something analogous to the 250 milliseconds that Libet talked about before that you were sort of decisions were starting to be made before you sort of realized it. Okay, so that does happen in this as well. But to say that your unconscious processors are not important in as it's part of the whole consciousness that your unconscious processors are putting something in. And so to say that it didn't get on stage yet, that decision was put into the process before it got on stage. Okay, that's true, but the whole ensemble is the consciousness, really. And I think that's making this clear. Those unconscious processors are really important for your consciousness, and they're working very hard. I mean, it's sort of like what I call the Poincaré effect. There's this very famous story about this mathematician Poincaré, who had been working hard, very hard, day and night on a hard problem. And he said, "I'm really thankful. A friend called me up, said, let's go on a hike." And then he says, well, he's getting on the bus to go to this hike. And he says, the moment he put his foot on the bus, the step, the idea popped into his head that these theories that he'd been working on, but he never saw that their relationship was they're perfectly isomorphic. Okay. That's because your his unconscious processes actually had, it wasn't like they were void of information. He'd been working very hard. Their information was there in their memory, in the long-term memory processes memory, and they were working hard through their links and unconsciously.
There's another example of this, which comes out of that story that Lenore gave. You know, you don't remember the name. What's her name? And you really would like to have that name, but it's driving home that suddenly it pops into your head. And what's wonderful about this is it shows you that some processor has been working on it. It's coming up long past the time you needed it, but it's clear that some processor there has been working on it and finally got the answer, and it gets broadcast.
To discount that as part of your consciousness is really a mistake. And I think that's where the misunderstanding comes in. I think that's really this misunderstanding. The misunderstanding that you make decisions before you're consciously aware of them, and there's something really crazy going on. That's the argument against free will. The argument against free will is that you have no control over that because you're not conscious of it. The decision has already been made, and then you're conscious of it. But no, that whole process is part of the consciousness ensemble. Unconsciousness is part of the consciousness ensemble. And I think that is the misunderstanding. And that when we talk about the conscious Turing machine, it's an ensemble. And it's the whole thing. It's not just that gets on stage and you get conscious attention when the long-term memory processes receive the broadcast. Yeah, we're calling it conscious attention, but it's the ensemble that's important and part of the whole process, the process. And I think that's a misunderstanding. It's the process that's important.
I think also relevant to this picture and particularly to Labat is he's looking at things from a bit of a different perspective, but there is a neuroscientist at Dartmouth named Peter Tse, who I spoke with quite a few months ago, who, well, from his perspective, he thinks that we have second order libertarian free will. So the capacity to also choose, not just choosing things, but to be able to basically choose what kind of chooser you are going to be in the future, essentially, that self-manipulation. And he's got this account of mental causation, which is kind of interesting. And he looks at it from more of a mechanistic perspective and also perhaps a little bit against the Labat experiments that you're talking about, or he's against the conclusions that they have about free will. And I don't know that I fully buy into the conclusions that his picture has, but he does think that mental causation is about something like changing the physical basis of possible future mental events. And he thinks it happens via rapid synaptic reweighting, which I think could look something a little bit similar to what your picture proposes in some ways. And so this kind of middle path he tries to navigate is that the brain can then set criteria for future mental activity that will be met by future inputs. And this can follow long periods of consideration or playing things out virtually in one's mind. And then you eventually get this maybe optimal set of criteria, and that gets wired into the synaptic weights so that the system is ready. And this is something like maybe a bunch of train tracks throughout a country or something. An analogy to this is something like changing those train tracks. He connects this to, I think, William James's theory of free will, because he thinks that this occurs in two stages, where the first stage, many possibilities are generated possibly randomly. And then the second stage selects the good ones or deselects the bad ones by some sort of will. I don't know if I'm totally with him on his picture actually gets us free will in the way he wants it to. He also has lots of interesting things to say about Jake Won Kim's exclusion argument, if you're familiar with it, and kind of the physicalist aspects of thinking about consciousness and mental causation. So he has lots of interesting things to say there. I don't know if I buy that he gets us all the way to free will in the way that he wants to, but I think he does paint a really interesting alternate picture that it strikes me has some analogies with what you're thinking about as well.
So I think that this is very similar. I think our explanation is a little simpler, but similar. And I think Manuel has a very good argument how in terms of playing chess that's similar to this, and I think he should give
So
it. But I
I'll explain it.
but
I'll
one sec, I
explain it.
won't
So
say it, but let me just say one thing before you tell about the chess, okay? I think, we have in our machine that we have this kind of dynamic of what we call predictive dynamic, predictions, feedback, and learning. And this is very important globally in our machine and also in the processors themselves, and even the processors that are making world models. And I see what he's saying is things that you're doing, creating, that he's sort of saying we're creating some potential predictions or possible future scenarios in our world model. We're trying them out, figuring which one works best for us and what we want to be. Yeah, and those are all being worked out in the world models. I think that's very much what he's sort of saying. So it's very consistent with. I think you could translate some of that into our world model, world processor type of thing. But I think Manuel has an excellent way of explaining it.
hold on. So Lenore brought up prediction, and that's really important because in the CTM, every processor that is putting a chunk into this competition has a prediction of the effect it will have. Every single chunk always is predicting what will happen and fixing its model to the if it works, great. If it doesn't work, fix the model so that the predictor is better. And so prediction is very important. And I guess, Lenore, you point out it's prediction, feedback,
I call
and
it
the learning.
predictive dynamics. It's sort of the role of predicting, getting feedback, and then learning. Sort of making, a lot of people call it correcting errors, prediction errors, or there are lots of different ways, and that's one of the things which we say we align with this thing. But we just simply say predicting, feedback, and learning. It's sort of a cycle that happens.
So let me go to
But
the
yeah, so
chess.
here's chess.
I basically I want to go to the our understanding of free will, and so our understanding is this um, that when you have a decision to make, when you are faced with a decision, uh, as you are in chess, you're playing a game of chess, and you will find that the next move you either should move this bishop here or the knight there, and you don't know which is better, and you have to actually go through some work to see which one is the right move to make. And our explanation for free will is that during this time, from at the time you realize that you have this decision to make, you don't know what the consequence of that decision will be, but you're open to whichever turns out to be the better decision. And the fact that you're open to it is what gives you the sense that you have free will, that you are free to choose. And the wonderful thing about this explanation is also that it really works even in a completely deterministic world. There's a Newton's world was deterministic. There's a game due to Conway called the Game of Life, and it's not really a game. It's what it is you have a checkerboard, a very infinite by infinite two-dimensional checkerboard, and uh, the cells in this checkerboard can either be alive or dead, and there are certain rules for whether a cell dies or is born or lives. There are certain completely deterministic rules, and the wonderful thing about this particular game of life is that you can build into it a Turing machine, a computer, a universal Turing machine. You can build into it a Turing machine that can self-reproduce, a self-reproducing Turing machine. And in fact, so that in fact, within this, and it's completely deterministic because the rules are, it doesn't have, there's no quantum involved. There's no question at all. It's if you set this thing up with entities that, and you can set it up so the world is very much like our world with entities that talk to each other, and so on. And within this world, God, we who created this world, know from any state of the world what the future will be. But within the game, two players who are playing chess, when the player has to make a decision between moving that knight or moving the bishop, that player doesn't know what it will do. We know, we can tell what it will do, but it doesn't know. And because it doesn't know, when it needs to make that decision, it is free. It knows it is free to choose whichever actually turns out to be the right thing to do. That I've explained this to people, and lots of people say to me things like, "Well, that doesn't explain to me why you would put somebody. What to do about somebody commits murder? Why do we put them in jail? They're not responsible." And but actually, we put them in jail because we don't want them to murder us. If they commit murder, it's better to put them away so that they don't hurt us.
So, Manuel, what you're saying is that we don't have free will, but we have the feeling of free will. Is that what you're saying?
Right. We have the feeling. You even in this deterministic world, the entity that has to make a decision will feel it has free will because it knows it will choose whichever it turns out to be the better for it. Yes. So the solution to Samuel Johnson's paradox, yes, we agree with Samuel Johnson, you do not have free will. But on the other hand, you do you do experience this because when faced with a decision, you are free. You are free to choose whichever is best for you, and that is what we call free will.
The best for you part is particularly interesting because one's awareness and ability to come about what option might be best can change over time. So, in your chess example, for instance, if I try to put this into your framework and think about the sleeping experts algorithm and what kind of comes into short-term memory and the eventual decision you make and the computation of that, I can imagine over time a beginner chess player in their own experience is just not going to attend to all of the same things and, to your point, evaluate them in the same ways, maybe weight different options in the same way that an expert chess player faced with the exact same situation is going to. And so I can see, it feels to me, I guess, like you have this consistency with, for both the beginner player and the expert player, they both have that in their head. I'm going to choose the best thing, but what's available to them in the form of perhaps the long-term memory processors, what's available to be attended to, what's kind of enveloped in their conscious, non-conscious experience. Those are going to look very different, is how I think your picture would put it.
Absolutely right. Yes.
Yeah, and I think what you picked up, which we haven't been explicit about, is the role of TCS, theoretical computer science, in this. Now, theoretical computer science, how that modified at least what might be called the theory of computation, which comes out of recursive function theory and Turing, and how it modified it, it was to take resource limitations, time and space, into account. And even though certain problems were in principle solvable, or decidable using the theory of computation model, in fact, they appear to be not feasible when you take time and resources into account. And that was sort of a distinction in the 60s when this TCS sort of started. With Manuel was one of the people who was looking into complexity theory of computation. So complexity in terms of time of computation. And that was a big sort of change in the view. And that's really, when we say theoretical computer science, it started in the 60s, even though computation starts like in the 30s, theory of computation.
Let me go back to this free will. The problem's been around for a very long time. I mentioned Samuel Johnson, but it goes way back. I mean, Plato talks about this same problem. And you might ask, why didn't why has this problem been around for so long? Why has this paradox existed until now? And our answer is that it did not occur to them to take time into account. That the fact that is, when you have a decision to make, the result is not instantaneous. You don't immediately know. It takes a while to come to your decision, and during that time you are free to choose what you want. That simply did not occur as an important feature of the previous thinking about free will.
And time is also a limit to space. So that's where resources, I like to say time and space. You're sort of pointing out the novice chess player and the advanced chess player. One has more resources than the other, and can access, and within the time can access more information than uh, the starting player. So that's where resources are really coming in here, taking resource into account. Now we take resources into account in a lot of things in this CTM. For example, in the chunk of information that each processor puts into the competition, the main feature in there is what we call a gist. And that's really the question, like, what's her name? And that has to be fairly succinct. It has to be fairly succinct because if we're going to do this competition along the way, and the computation for the competition, who's going to win, it has to look at that gist. And if the gist is too
Let me
long,
just for a second,
go
just
ahead.
quick interrupt to explain what a gist is. When you have a dream, you know that frame that you see, that's a gist. That frame is
It's a
represented.
multimodal. It's a picture, it's a sound, all this. So, but that just has to be fairly small. It's sort of, and so because if you're going to do computation on it, which needs to be fairly fast, it's got to be small, so it limits the size. So that's where sort of resource limitations coming in. The fact that the competition has to be fairly fast is coming into, you don't want to make, you want things to be very quick at each stage that you're making decisions. So a lot of that's coming into the way we've built the model, actually.
And that frame, so I mentioned that when you have a dream, a frame is a gist. And you may have, in that dream, you may have trees and cars and people and stuff, and it seems like a lot of information, but that actually is encapsulated in a brainish word, the gist, in something very small. And there's good reason to believe this because so Lenore often shows this uh, the example of the going. I'm thinking of the one where the detective comes in and sees these people and talks to and tries to find out who committed the murder. And you see at the beginning, you see this living room with a person lying on the floor, dead, and the maid. The other people there, and the detective and the policeman, and that's what you see, and that's all that your gist has. So that at the end of this beautiful film that Lenore shows, uh, you get a picture that is represented by the same gist. It still has the man on the floor, but he's now wearing different clothing, and his knee is up in the air. And the detective has a different color of clothing, and lots of things have changed, but the gist is still the same. It's a living room with a detective and these people and a man lying on the floor, and that's all that. And the people don't notice that the change has occurred because in fact that very small gist is what you know about what's going on there.
So it's a way that our CT. So we have a number of examples where the CTM can exhibit phenomena that's often associated with consciousness, and we go through several of these in one of our papers and others. So we have a whole now really long list of phenomena that at least our CTM could have some of these pathologies or can experience certain things like this. Blind sight's another one like that. And the one that Manuel was talking about has to do with why, the short gist is really what's happening in humans too. Humans aren't keeping a whole lot of information, and so you have to have a way of encapsulating information in a very short description. And so this also goes back to the 50s, George Miller, the psychologist, who said that, the magic number 7 plus or minus 2 is all, we couldn't hold a whole lot of information in our short-term memory at any moment of time. And that's capturing actually the fact that the gist has to be pretty small, pretty succinct. He's saying you can have 7 plus or minus 2 chunks, basically. We're saying one chunk. And in fact, we can simulate 7 plus or minus 2 if we wanted to, but we want it to be simple. So, but nevertheless, it's the CTM again is consistent at a high level with a lot of thinking, over the years also by the psychologists and philosophers. And this person, I would actually wanted to get the name of this person at Dartmouth because I think they sound like a philosopher or a psychologist with a very complicated but right analysis. And I think we have a similar thing, but a little, maybe naive, but shorter.
What's his name? What's his name?
His name is Peter Tse,
Oh,
Tse.
yeah, he has written a book.
Oh, yeah, good. I heard that.
2013, yes, a while ago. He certainly talks like a philosopher. I will give him that. He's a neuroscientist. The story you told me is he initially wanted to study physics and mathematics and was very interested in some very lofty theoretical questions. And then eventually, I think that understanding the universe felt a little bit out of bounds for him in some sense. And so he scoped his question down to, okay, let's understand the human brain and do neuroscience.
Being nice and small.
Yes, it sounds like the physics was also complicated, but the math is kind of math is kind of nice because you can
you can get your hands around it.
Sort of. If you want to live in that world where your head is like going around these formulas, whatever. But yeah, it works for us. It's what works for people. This works for us.
Yeah, there were a bunch of things coming up for me as I read through your descriptions and the kind of various examples you list. And dreams is always particularly interesting to me. And I think there are elements of this that connect with our discussion about language earlier, because there's something about our experience of the world and maybe our experience of dreams even. Like dream logic doesn't seem to work in the same way as everyday logic. And when you look at popular attempts to describe the way in dreams work, you get stuff that looks like a Miyazaki film or the writing of James Joyce or something, where you have to bludgeon language into submission almost to return from, I had this experience of the world and then I now need to use the language I have available to communicate with other people, and I want to maintain some kind of fidelity to the experience I'm having of the world during the day or during the night in my dreams. And then you get something like Finnegan's Wake. And it's hard to do anything with it because all you have available to you is the words and this kind of compressed, weird representation of what was presumably going on in a dream. But like the transposition and the almost violence you have to do to language to make it to afford some real fidelity in that medium to the actual experience of a dream or even the experience of daily life was really interesting to me. And so I guess I'm thinking a lot about how your picture interacts with that and what seems to go on there.
Yeah. So one thing that comes up in this dream is since you don't have the real world giving you feedback, my sense is that it's not that the logic is different, which you mentioned, as much as the fact that you don't have feedback. So you can't really fly. You can try, but it doesn't work. But in the real world gives you feedback that keeps you from doing it. But in a dream, you don't have that feedback, and you can fly. I don't know if that's what you meant by logic, but there is this fact of not having feedback that accounts for the fact that when you're in a dream, you don't realize you're in a dream.
So I would say something also that occurred to me when you were saying this, Finnegan's Wake. So yeah, in our model, dreams And this internal discussion in the CTM is all done through this multimodal language. And so these frames and dreams are multimodal. And then when somebody is trying to translate that into linear language, it becomes very convoluted because you're taking this multimodal fusion of all of these senses, all of these possibilities, which are multimodal. And then you're trying to string it out into a linear language, just one of the linear languages that has to express, the feelings, the sounds, the smells, all of these things that you didn't have to say in words because it was, in English words, because the multimodal words were so rich. So I think that, and so that when Finnegan's Wake comes out, it seems so convoluted because this is a mechanism of trying to translate this multimodal fusion into a linear language. I think that's what's happening.
That tracks with how I thought about this from your perspective. And I suppose it's also interesting just to think about the perspective of trying to disentangle the various parts of experience that kind of come together into this multimodal language. Because one thing that a lot of people in, for example, machine learning who are thinking about, for example, representation learning and stuff like this will look at is, are there ways to disentangle the representations that come from maybe various data sources or things like this? And we also have these kind of new multimodal models that are not something like the Conscious Turing Machine, but have their own takes on the kind of clip strategy, for example, of I can deal with vision and language by encoding an image, by encoding some caption for that, and then I can project these into the same dimensional space and do some interesting things with that, with contrastive learning. And that was a very interesting strategy from OpenAI. And one thing you notice, though, is that there's a blending there where you lose aspects of compositionality, right? Clip does not understand the difference between man riding a horse and horse riding a man, for instance. And this kind of comes across through that process of, I have this fixed caption and then this fixed image that it corresponds to. And so the embeddings of these things are all I have access to, which is interesting. But I suppose it feels, when you're talking about a multimodal inner language that is actually capable of handling all these distinctions, it feels harder, I guess, to track I can move forward from all of the experience I have with the world, all the various processors, into some representation in this multimodal inner language. But then to what we were just saying with attempts to characterize or describe dreams in language, going the other way and disentangling all of that feels very hard.
So I think they're both not, I think, straightforward how you fuse them and how you fuse them so that, the horse on the rider on the horse on the rider, so that you have the right kind of composition. So that's part of the fusing, and then then the disentanglement is also hard. I think they're both hard. There's
I mean, the disentanglement comes in part because there's a broadcast, which is of a gist, which could be this gist of the living room with all what's going on there. And then there are these processors, and each processor can look at the part that interests it or that it knows about. That's where the disentanglement is taking place.
So this is in theory in our model. Now, to make something like this in practice is a whole other thing, and we're sort of theoreticians, so we can get away with it. But we have been working with a PhD student at Carnegie Mellon who actually just got his PhD actually a few weeks ago, Paul Yang. And so you can think of the CTM as a framework. And what we're trying to do with Paul now is maybe to get a blueprint a little bit better. And so what Paul's an expert in multimodal machine learning, and seeing if we can sort of get some kind of a blueprint to get some kind of maybe even toy model of a CTM going using that. So I think the going from the theory to the practice is that's a whole other jump too. We're trying to look at what's important what's key and sort of give the framework. But I'm not going to minimize the difficulty of implementing something like that.
Although I have an idea of how to go about it. So, uh, we haven't explained what goes on in each processor. Every processor has in it a bunch of stuff that it knows about. It has to do the prediction. It has to compare. It has to fix the model it has. So each processor has stuff in it, and we haven't in our CTM said what that stuff is. But we have said everything else. And so my sense of what should be the right first model, it would be to build the CTM with processors which are many copies of ChatGPT and many copies of Google and Wikipedia and language translation and dictionaries and calendars. Basically, all the stuff, all the apps that you have on your iPhone, have them be available as processors, and they're ready made. So you don't have to talk about what's built into each processor. If ChatGPT says the product of, I give ChatGPT the problem to multiply 1, 2, 3, 4, 5, 6, 7 times 7, 6, 5, 4, 3, 2, 1, and it cannot do it. It will give you the first few digits correctly, the last few, and the stuff in between fails terribly. But if in this model, if ChatGPT were to suggest the answer, another processor that's a calculator could come by and say, no, here's the answer. That's wrong. And so that would be my that's the what I would like to build first. The CTM I would like to build. Use apps as processors, and everything else follow the rules.
That's interesting to me because when I was reading your AI consciousness is inevitable paper, I think that you also articulate this in the form of a conscious Turing machine robot. And that's interesting to me because one of the big questions that a lot of people who are thinking about philosophy of language or just things around AI right now are wrestling with and once again discussing is stuff around symbol grounding and the Chinese room argument and meaning and how that comes across in words. Stefan Harnad, who famously wrote the 1990 symbol grounding paper that articulated a lot of these problems. How is it that symbols in our heads come to have meaning at all? He very strongly believes that you need what he calls T3, which is you have something that doesn't just pass the Turing test in language, but actually passes what he calls a robotic Turing test. And this is what he calls T3 essentially. And he thinks that this component is actually crucial for words to come to have meaning. So I guess it was interesting to me, Manuel, that you said, let's start with. But it does feel like if the whole meaning question and things like that, how words hook onto the world is something you're interested in. I don't know if you two have thoughts one way or another on the grounding question or if that's something you're even interested in. But it was interesting to me that you were talking about like the conscious Turing machine robot because it felt like it evoked a lot of that.
Right. So the idea to talk about it as a robot was to really acknowledge that a lot of our consciousness comes from what I call the four E's, or what people call the four E's: the embedded, the embodied, the enacted, the extended. That we're embodied. We have these sensors, and that's going to be part of our. It's not just the brain in the vat; it's sensors. That bringing information in. There are actuators that we can act in the world. We can walk around. We can do things. So that's embedded, embedded, enacted. Also means that we can change the world. Also, we can do things to affect the world, and these robots will be able to do that. And the extended one, which as actually Chalmers and Clark talked about that a while back, saying this is before ChatGPT or before even maybe Google. They're saying, well, we have libraries. You go to libraries, and that's extending your mind. And now we have all of these internet things like Google and Chat and all that. And so that's the extended mind. It's not too different than having libraries. Or going to universities or whatever. So that's just an extension of all that. And so what Manuel's saying now is that if we were going to implement that, why not take all of that into account? Whereas the theoretical model, one wants to start more with, really almost vanilla processes and see how they develop specialties and all that. I think that would
And that I would like to do too, but that's not the first. That would
in
not be
terms
the
of
first step.
that's not going to be
That's
the first
the
step in implementation. The first step in implementation is really to take advantage of all of this thing and all of the technology that's out there. But with the kind of architecture that we're sort of suggesting, and with certain things like this dynamics being very important, models of world being very important, multimodal languages, how are these different processes communicating with each other, having a common language, the vision processor with the vision processor with the speech processor with the sound, whatever. So that's where we're getting multimodal machine learning coming in. So we're sort of saying, yeah, when you're going to first, if you're going to implement this, take advantage of everything you have that is already developed that will work on this, and we'll get to the same problems that most people get to when we, except that we're making some kind of more global suggestions that may be interesting to implement, not having a central executive doing things. That's sort of what I would say.
I'm curious, when you two think about AGI, are you just thinking about, I suppose, the standard definition that most people have in their heads of something that can do a large collection of tasks better than most people or something like this? I'm curious how you two think about it because it's a very loaded term at this point in time.
exactly right. Yes, that is what we're thinking. We're thinking that each processor is itself an AI processor. ChatGPT is a processor, a very powerful processor. Each of the apps is pretty powerful.
I suppose a related question here is I'm curious how you think about the role of, especially in the initial versions of a system like this. ChatGPT on its own is, of course, not going to be the full system. It's one component in it. But there is a lot of debate back and forth these days in the AI community about how far scaling laws are going to take us, what happens when you 10,000, apply 10,000 times as much compute to something like ChatGPT. And presumably that's going to make it a lot better at doing many of the things it does and maybe other things we haven't predicted. And I'm curious how you would think about just in imagining what initial implementations of a conscious Turing machine or an AGI would look like on your picture, how you would work through or think about the implications for, well, ChatGPT is like one processor in this larger system. So what happens when it maybe becomes a lot more powerful? I also wonder if you two have any thoughts on this debate at all, or if it's something that you've been interested in.
So, just one point is that one of the processors is ChatGPT. Actually, quite a few processors are ChatGPT. So, when a question is asked, each of these ChatGPT processors can come up with its own answer. And one of them will perhaps get up to the stage, and everything goes as we have said. Uh, so yes, ChatGPT is very powerful, and it is a processor, and we're talking about having 10 million processors, 10 million, corresponding to the 10 million cortical columns in our
So
cortex.
I think one thing I think is that we can't. So I think what people like Jeff Hinton happened to Jeff Hinton is he knew that these systems that he was developing, deep learning, would be powerful. But I think it never dawned on him how powerful and how quickly they would be. And I think that made him pause. And I think there is a sense here that the kind of intelligence and the consciousness of these machines, because in fact, I do believe some of these large language models actually are making world models because they are getting, and they are more like the CTM than not, because they're getting input from every human being who's using them, right? They're getting, if they're implemented in robots, they're acting in the world. They're actually doing really getting much more than just looking, scouring the web and predicting next word. They're doing a lot more than what. For one, actually, I think it was so amazing to people how powerful it is at predicting next word.
But it's not just predicting next word, of
Yeah.
course.
If you had such a huge corpus and such powerful computation, predicting next word is so remarkable. I think nobody understood that. And I think people like Jeff did not understand that so much.
And people like Bernie Bars is actually very much afraid of this. So Bars has, uh, we like Bars. I made it clear. I really thought his model was wonderful. He hates us
I wouldn't say he
because
hates us, but he really doesn't want to support the work we're doing because he's very afraid of where it's going. And I think, and I think that there's, I think as being, we're not even like Hinton, who is actually developing, large programs. We're actually at the paper and pencil thing. I mean, we don't do more than write papers or, write on, scribble with pencil or whatever. We're not even actually programming ourselves or anything yet. So, um, we're sort of,
hey, mathematics is pretty good at giving understanding. That's what.
well, we are really trying to understand. I mean, I think that's our motive, was to understand. But the fact is, the more, this is a framework which could develop into a blueprint, which could do that, and that's true. Even though our motive, Manuel's motive was to understand what's going on in the here. Wow, and that was really our motive. And we're using, computation to understand that. And once we do that, it's closer to being implemented than philosophers who are trying to understand it without even doing it kind of a mathematical
Well-defined
model.
mathematical model.
Right, right. So we're a little bit, more in sin than the philosophers, I think, because we have something that they can. Uh,
We like the philosophers. I mean, we especially like David Chalmers. So
whom we actually, I think for me, the two philosophers that I love the most is Chalmers and Dan Dennett, who, just passed away. But I feel closest to their views. They don't always agree, Dennett and Chalmers, but I think we have a bit of both of them in how we're doing, how we're going about things. Um, yeah. So I think we can't be just the mathematician saying, well, nothing like, it was the mathematician who said the number theory
hey,
doesn't
we're
make.
being the theoretical computer scientist who makes a model and fixes it and then proceeds by trying to understand what that model can do. Just it'll help and it'll be correct in some ways. It'll be wrong in other ways. The problem right now is the model seems to explain a lot. Let's fix it. We fixed it, and now let's understand what it can do and what it can't do.
Yeah. So that's
And
where
that's
we are
something that
actually
we
personally.
theoretical computer scientists do.
Yeah. So that, I think, is our focus right now, though these other implications are obviously pretty much obvious. The implementation seems pretty much out. But our personal saving grace is that we're not programmers and we don't have access to huge machines. But
Wait. If we don't get somebody to program this thing, I'm going to do it. I I
before anybody
absolutely
had computers, Manuel built us.
okay. So it's easy to build a Turing
I mean,
machine. So
he's an engineer and he taught classes on how to put these circuits together. Remember, Manuel?
I guess that's right. But my sense about the build about the circuits is that even if I were given the circuit diagram of the brain, exact statement of how these neurons are connected, what the chemicals are, everything about how it works, I still wouldn't understand. That's not enough for the understanding I want. That one of the reasons for this very simple model and just trying to see what it can and can't do mathematically is because it gives me what I feel I want, the understanding I want.
So what we're trying to do is isolate the key functionalities that at least we feel are important for consciousness. And we're trying to isolate. We're not saying how those functionalities would be in, in the brain, particularly, even though we are influenced by the neuroscientists. We're looking for sort of basic functionalities that would be important, not necessarily how they're implemented. Um, I wanted to say one other thing here, though. But, what? What? I was thinking of Hardy before, but that's not.
This does accord with the grasp I had of what you were looking to do. And I guess it's interesting that you had mentioned Hinton earlier, because I guess, I sense a different posture, I suppose, towards, well, not necessarily a different posture towards the implications of the systems, but just a very different energy from the two of you about that. Because with Hinton, it was this sudden shift from, I don't know, a lot of talking about how AI is going to replace radiologists over many years, and then suddenly, or maybe not so suddenly, I'm sure it had been on his mind for a while, but there was this shift over to, oh my God, these systems, this could be very dangerous. And it was interesting to me to see the same with Benjio as well, because I think I actually interviewed him on this maybe a couple of months before that moment came along where Benjio officially seemed to be in the AI safety camp of things. And I didn't sense that from speaking with him at all about it. So it was very interesting, and it made me wonder.
You didn't sense what? That
I couldn't have predicted that a couple of months later he would be very much in the AI safety community worried about existential risk from AI. And I guess it's worth noting that our interview happened before the ChatGPT moment, and it did seem like that was the thing that brought it to a head for him. It was interesting, I guess, just to contrast those with the way that you two seem to be thinking about the conscious Turing machine and your own efforts and those implications, because you are seeking, as you said, something that is more like understanding, and you do want to implement something like this, but it seems like the do you two feel like there's anything analogous in these sorts of systems you're interested in? Do you feel like you have any analogous worries for your conscious Turing machine and things that you're thinking about?
let me come at it from a very different viewpoint. I was once a member of the Miller Institute, and I remember there were a dozen professors having dinner together. These are professors from many different parts of the campus, and physics, chemistry, certainly many sciences. And the question came up: how long before we have destroyed ourselves? And it's very interesting that the numbers that came up were between 50 years and 500 years. A dozen professors saying we're going to survive for another 50 to 500 years. And that's it. And this was 40 years ago. It certainly gives my sense is, you know, uh, maybe these computers will destroy us. It's perfectly possible, but I think it's our only possibility to save ourselves. Uh, uh, we will. They may destroy us, but at least there's a chance with them that we may survive. And I view them as our progeny. So people don't like that either. But I do view these computers, these chat GPTs, and what's coming after them as our progeny. We have created them, and they will be a lot smarter than us. And whether that's a good thing or a bad thing is very hard to tell, right? They'll be a lot smarter. Yes, Lenore.
Okay, so I think that's really worthwhile, noting how Manuel views this, that, that these machines will be our progeny. That, and in some sense, that's one reason to understand what they're capable and how they're doing it. But I'd like to look at a slightly different aspect of, I think, what you're asking. Um, so a couple of weeks ago, there was this New York Declaration of Animal Consciousness. And this was an update on, there was a Cambridge Declaration of Consciousness in 2012, so more than 10 years ago. And I think we're becoming much more aware of consciousness in the animal kingdom than we had been in the past. And there's a lot of awareness of, how one treats animals because of that. And I think a very similar kind of thing is really warranted. And I think coming out now with AI consciousness, the potential. And the AMCS, the Association of Mathematical Consciousness Science, we wrote a letter, an open letter, so about a year ago, actually, now. It's called, I have it here, the responsible development of AI agenda needs to include consciousness research. So really putting it on the table, and this was signed by maybe about 200 top people, including people like Bengio and us, saying that consciousness research is really important to understand what the implication is when we're developing these AIs and what to do about it. And then the AMCS also, there was a call for the United Nations also has a commission on AI responsibility and all that. And we submitted recommendations, a paper called Recommendation to the UN High Level Advisory Board on Artificial Intelligence. And we've said it should include consciousness. And that paper was accepted by the UN. So there are organizations and people, who prominent people who are really raising this as an issue, saying that, at least we should be thinking about this. So it's coming up it's coming up in the general non-human consciousness world, both non-human animals and also machine consciousness. And I think people are aware. Now, I think there has to be, discussion by people like us. I think we have to be involved sort of to really deal with the kind of hyperbole that's coming out now too, and the fear that people have. And I see it as a really teaching moment, a teachable moment now too. I mean, I don't know whether we're the right people to do that, but I think good people are, involved, thinking about it, and seeing the value of looking at consciousness, understanding it. So there is maybe it's self-interest to say there should be more support of consciousness research. Yeah, so that could be self-promoting, but in fact, it's really important to understand these issues going forward. Um, so I think all I'm saying is that's a little different aspect, where the consciousness community is becoming more involved in being publicly concerned, as the AI community, like Bengio and Hinton, becoming publicly concerned. I think they're very intertwined, these two groups, um, and with the animal consciousness. Well, first of all, I want to say, Daniel, this has been really fascinating for me because your questions are absolutely super, and you're also giving us some really interesting people to look at and things to look at. So that has been great for me.
Very much.
Yeah. Thank you both for being so generous with your time. Maybe a good place for us to begin closing out would be something like, I think what you just said is very interesting to me in lots of ways, and partially because I'm thinking about there's a lot of bewilderment right now, a lot of wondering, especially from younger people who might be growing up studying computer science, becoming technologists. And it's making me wonder what the two of you would say to, I don't know, a hypothetical 26-year-old engineer who may or may not be speaking to you right now, and is thinking a lot about these questions of how does one be the sort of technologist who is able to leave the world a little bit better than he found it and to really contribute something. I'm wondering for younger people who might be listening to this, doing PhDs, starting out their careers, how you two would think about, I guess, in a time like this, how they should be understanding their place within the world, how they should be trying to use their careers for something useful. Like, what would you like to see from younger people, I think is maybe what I'm trying to ask.
When I talk to students, I mentioned that when you're born, look at the intelligence, the ability of the person as an infant. That ability grows very quickly. 6 years, they're 15 years old. They're high school, college, and from then on, and then uh, graduate school, and then assistant professor, and professor and then emeritus. So I remember Warren also thinking the kid is the smartest when he's 12 years old. That's when you're at your pinnacle. And I met Lenore when she was 10. She was in the fourth grade. So I know what it's like to be in the fourth grade.
I wasn't in the fourth grade. I dropped out
So
of school
don't
when I
go
was in
into it.
fourth
Don't go
grade.
into it.
So I
I
spent
was
the
in the
whole
fourth grade
year
when
having fun and not being in school. But I would like to say, so I'm a kind of mathematician scientist at heart, and I think that you're most powerful if you understand some disciplines well. So, I mean, you have to be aware, but I think you can be more powerful if you're okay. I would say study mathematics, study neuroscience, study philosophy. If I had my druthers, I would, if I had many more years, I would start all over and go into neuroscience and learn that much better. I have a high level understanding because it's so fascinating. I would learn, or I would go very much more deeply into mathematics or physics or something like that, because I think that you become much more authority. You speak from authority. I'm not saying be narrow, just, but I think you have to be somewhat deep so that you can actually speak from rather generalities. I think we all have these general things that we want the world to be better and we want things to be good and not to be harmful and whatever. But the way you can make change is by being an expert in some areas also, where you can use your specialness to make changes, where you can use your a lot of this is really dealing with, so with consciousness, for example, if we understand it better, we can deal with mental health, for example, problems. A lot of this we've seen in the CTM, even how the CTM could experience, all sorts of very strange phenomena,
we didn't get
paranoia,
into how the CTM
depression.
actually experiences pain, but the understanding from that is can be helpful.
Pain, it would be wonderful if one could really understand it, but depression, so many of these, so there is very interesting implications of all of these things, but you have to come from some level of expertise also. So I think interdisciplinary is totally great if you're coming from a disciplinary. Interdisciplinary with a discipline would be the way I would go. So whatever strikes your passion, go for that, but also broaden it with some interdisciplinary perspective. Um, but if you're just a pure scientist at heart, just go for it and delve into it. And that's the exciting thing to do. And you can be very powerful that way too. So disciplinary with an interdisciplinary overarching.
Good point made.
I think this is a great place to end. I appreciate you both taking so much time to speak with me. It was really an honor. I appreciated all the stories and the explanations and everything. It was.
Yeah,
Thank you
I appreciate it too.
Thank you as always for listening, and thank you to my guests, Manuel and Lenore Blum. I'll see you next week.